There's a star out there you can almost see with your naked eye on a dark night. It's not some distant speck billions of light years away. It's practically next door in cosmic terms. A star harboring a planet that might support life. Proxima Centauri sits just 4.24 light years away. That's approximately 24.9 trillion miles from Earth, the closest stellar neighbor beyond our own sun. In astronomical terms, it's practically next door, a cosmic stone's throw away, and yet humanity will likely never set foot there. Not with any technology we possess today. Not with anything we'll develop in the next century. The distances involved are so catastrophically vast that our fastest spacecraft would require tens of thousands of years to arrive. That's not a mission timeline, that's a geological timescale. Today we're examining exactly why reaching this tantalizingly nearby star represents one of humanity's most formidable challenges. And why, despite the seemingly short cosmic distance between us, the journey remains effectively impossible, at least with anything resembling current propulsion technology. Our obsession with Proxima Centauri isn't arbitrary curiosity. Observation using Earth's most advanced telescopes have confirmed that this red dwarf star hosts at least one planet orbiting within the habitable zone, Proxima b, a world where liquid water could theoretically exist on the surface. The implications are staggering. Potential life just 4 light years from Earth. The closest potentially habitable world we've ever discovered. And we cannot reach it. But can we actually reach it? The blunt answer is no. Not with current technology. And the detailed explanation is even more discouraging. Consider this sobering reality. Humanity hasn't even managed to send astronauts beyond the moon. The moon sits just 238,855 miles from Earth. Proxima Centauri is roughly 100 million times farther away. The scale difference is almost incomprehensible. Our minds simply aren't equipped to grasp distances this vast. Voyager 1, launched back in 1977, currently travels at 10.5 miles per second. That's approximately 335 million miles per year. Sounds impressive until you do the math. At that velocity, reaching Proxima Centauri would require over 73,000 years. Human civilization as we know it is only about 10,000 years old. We need to maintain a functioning mission for 7 times longer than recorded human history. Every civilization that ever existed would rise and fall multiple times during that journey. To make a Proxima Centauri mission feasible within a human lifetime, we need velocities utterly beyond current engineering capabilities. The bare minimum speed requirement is approximately 6,200 miles per second. That's roughly 590 times faster than Voyager 1. That's not an incremental improvement. That's a completely different category of technology. At that velocity, the journey would still consume around 125 years. Multiple human generations would live and die aboard the spacecraft. If we could somehow reach 15,500 miles per second, the travel time drops to 50 years. More achievable sounding, but we're still discussing speeds that remain pure fantasy with current propulsion systems. This forces us to completely abandon conventional chemical propulsion. Traditional rockets launching satellites and spacecraft today cannot achieve even a fraction of the required velocity. We need revolutionary propulsion systems that don't exist yet. Systems that exist only in theoretical physics, papers, and scientific fiction novels. This reality demands accepting some hard truths. First, we must abandon the idea of bringing astronauts home. Any crewed mission becomes a permanent one-way journey. Second, instead of attempting orbit or landing, we might settle for high-speed flybys, collecting data during rapid passages rather than stopping. What propulsion technologies could theoretically transport us there? Ion and plasma engines immediately come to mind. They've already powered several missions, including NASA's Dawn spacecraft. These engines achieve very high exhaust velocities, making them efficient for deep space travel. But here's the brutal problem. While these technologies represent impressive advances, they'd still require more than 40,000 years to reach Proxima Centauri. Marginally better than Voyager, but still impossibly long. A more promising development is the VASIMR engine, Variable Specific Impulse Magnetoplasma Rocket. Developed by Ad Astra Rocket Company under former astronaut Franklin Chang Diaz, the 200-kilowatt version could theoretically reach Mars in just 39 days, dramatically faster than the 6 to 9 months required by chemical rockets. But even with that remarkable performance, reaching Proxima Centauri would still consume approximately 2,200 years. Better certainly, but still impossible for any practical mission. We're still discussing timeframes that exceed any reasonable mission planning. Another technology sounding like pure science fiction but actually studied seriously is nuclear pulse propulsion, famously known as Project Orion. This concept involves detonating nuclear explosions behind a spacecraft using the blast to propel it forward. Reaching Proxima Centauri using this method would require approximately 300,000 nuclear detonations. That number alone reveals the absurdity of the engineering challenge. This idea was partially tested during the 1960s. Theoretically, using fusion explosions, far more powerful than fission, we could achieve significantly higher velocities, about 6.2 miles per second, representing roughly 3% of light speed. We're discussing a colossal structure weighing around 880,000 pounds, with a shock-absorbing plate 328 feet in diameter. Even with this extreme engineering, the journey would still require approximately 400 years. That might sound like an eternity, but it's actually somewhat realistic for a generation ship, meaning a spacecraft where multiple human generations would live and die during transit. Your great-great-grandchildren might finally arrive, assuming the spacecraft survives that long, assuming human biology can endure centuries in space. Wait, you're probably thinking, all this sounds completely hopeless. Maybe we should just abandon interstellar travel entirely. But hold on, because there are technologies that could actually work within decades, not centuries. Technologies that might let humans alive today see results from another star system. Another fascinating technology frequently discussed is the solar sail. Contrary to popular misconception, these sails aren't pushed by solar wind. Instead, they harness radiation pressure from light photons themselves. Japan's Ikaros mission successfully demonstrated this technology in 2010. The concept involves deploying a gigantic sail similar to a space parachute, capturing light pressure to gradually accelerate until escaping the solar system. Maximum efficiency requires positioning dangerously close to the sun, about 0.05 astronomical units away. The sail would need withstanding extreme temperatures exceeding 2,700 degrees Fahrenheit. Even optimizing everything perfectly, the journey would still consume between 1,000 and 2,000 years. Solar sails alone don't solve our problem. Some projects combine solar sails with nuclear explosions, like the Medusa concept from the 1990s. Controlled explosions generate radiation pressure against the sail, multiplying the propulsive effect. This hybrid approach could theoretically reduce travel time to around 400 years, similar to pure nuclear pulse propulsion, but with different engineering challenges. Perhaps the boldest evolution of sail technology is the laser sail, also called a photonic sail. Instead of relying on sunlight, this system gets powered by focused laser beams fired from Earth or orbital platforms. This overcomes the distance limitation of solar radiation. Lasers can deliver concentrated energy across interstellar distances. If we constructed a laser array generating 25 gigawatts of power, we could send a small 220-pound spacecraft to Alpha Centauri in merely 40 years. That's within a single human lifetime. Finally, we're discussing achievable timeframes. Obviously, everything comes with costs. The lasers would need operating continuously for 4 decades. Spacecraft mass must remain minimal, otherwise acceleration becomes insufficient. We're talking about probes, not crewed vessels. Breakthrough Starshot is undoubtedly one of the most ambitious proposals ever conceived for reaching the stars. Created by the Breakthrough Initiatives Foundation, funded by billionaire Yuri Milner with support from Stephen Hawking before his death. The project has already received over $100 million in funding. This isn't science fiction anymore. Real engineers are working on real hardware. Real funding is flowing into development. The concept is elegantly simple in theory, but revolutionary in execution. Send a fleet of microsatellites called Starships towards Proxima Centauri, propelled by the most powerful lasers ever built. Each probe would weigh just a few grams, equipped with miniature cameras, sensors, and communication equipment. A mothership would transport thousands into Earth orbit where they'd be released. Massive lasers positioned on Earth or strategic space locations would fire at each probe sail. The concentrated light pressure would accelerate these tiny craft to approximately 20% of light speed. That's 37,200 miles per second, roughly 3,500 times faster than Voyager 1, the fastest human-made objects ever conceived. At this astonishing velocity, each probe could reach the Proxima Centauri system in just 20 to 30 years. And since the star sits slightly over 4 light years away, data transmitted back would arrive at Earth approximately 4 years after collection. We could have actual images and measurements from another star system within 25 to 35 years of launch. During system passage, probes could fly by Proxima b, the most promising planet orbiting that red dwarf. Positioned roughly 1 astronomical unit away from its star, similar to Earth's distance from the Sun. Although Proxima Centauri is much dimmer, so the planet receives comparable energy levels. Since these probes would be extraordinarily small and fragile, collision risk with interstellar dust particles runs high. But Starshot compensates through sheer numbers. Launching thousands means many will survive the journey. Even if only a fraction arrives successfully, the mission succeeds. Redundancy through numbers. A swarm approach to interstellar exploration. What's most remarkable? This project, sounding like science fiction, could become a reality within the next 2 decades, assuming proper funding and technological development. With adequate investment, humans alive today could witness data arriving from another star system. Even if we don't discover worlds resembling Pandora from Avatar or encounter any form of alien life, a successful Proxima Centauri mission would possess immense scientific value. Observing planetary formation and evolution around a completely different star would revolutionize our understanding of how solar systems develop. It would transform our comprehension of the Milky Way and our place within it. Carl Sagan once observed something profound. He said that when we're finally ready to visit other stars, we'll no longer be the same species. Humanity will have transformed through the very process of developing interstellar capability. The technological, social, and psychological changes required would fundamentally alter what it means to be human. If we want to survive long-term, to thrive rather than merely exist, and leave a lasting impact on the universe, we must look beyond our tiny blue planet. Explore what lies beyond the familiar cosmic neighborhood. Take our first steps towards becoming a truly interstellar civilization. The technology isn't completely ready yet, but the desire, the determination, and the courage to attempt it, those qualities already define who we are as a species. The same drive that pushed our ancestors across oceans and continents, now pointing toward the stars themselves. We've explored why reaching Proxima Centauri remains one of humanity's greatest challenges, and how projects like Starshot might finally make the impossible possible within our lifetimes. Speaking of impossible journeys, did you know that traveling to Mars might also be a one-way ticket? The human body deteriorates so severely in low gravity that returning to Earth could become physically impossible. Check out my video explaining why a Mars trip might be permanent, where we explore the shocking biological reasons astronauts may never come home.